Okay, so thanks everyone for coming. So this is the second event of this new series of colloquia we organized here in Miramare. The colloquium series in theoretical and computational physics. So the idea of this series is to have a kind of pedagogical series of seminars. So we start with the basics and then we go on with more advanced topics. And for this semester, we decided to focus on machine learning in physics, machine learning science. So we started with Alex Rodriguez with an introduction about the topic. Now Professor Laio will go a little bit more in depth. And then we will see how these machine learning techniques are sort of applied in different areas of physics, from climate physics to cosmology to particle physics and so on. Until June. June will be the last event. So a brief introduction to Professor Laio. I mean, 90% of the people here know him, but especially for the students and for other newcomers, and maybe a bit of interaction with you. So Professor Laio is a professor in statistical and biological physics at SISSA here in Trieste. He's also scientific consultant of the International Center of Theoretical Physics, ICTP. He got his PhD in solitary physics at SISSA back in 1999. And after that, he went to ETH in Switzerland for 6 years of postdoc, where he worked on first on the development of a multi-scale approach to molecular biochemistry, and then on the development of techniques for computer simulations of rare events. So between 2016 and 2019, he has been president of SICAM, Lausanne, the headquarters of SICAM in Lausanne, and he's the author of more than 130 articles in well-known international journals. In 2002, together with Michele Parinello, introduced metadynamics. So that is a powerful approach to explore free energy landscapes characterized by metastability. And at the moment, his current research efforts are about the development of machine learning techniques for analyzing complex data landscapes and the development of algorithms for enhanced sampling in molecular simulations. Okay, and here is most important contribution, so to say, is the density peak clustering, which has been published in 2014 together with Alex Rodriguez, who gave the first talk about a month ago. Okay, and so without further ado, let me just thank a lot Professor Laio for accepting our invitation, and the floor is yours.
Thanks very much for the invitation. It's always really a pleasure to speak here. So this is focused on the description of classes of approaches which we have been developing over the years, which are in a way motivated by a pretty specific problem which actually arose over the years as I was doing molecular simulations. So if you do molecular simulations and at a certain point, due to the fact that the computer become more and more efficient, and moreover, people around start developing enhanced sampling methods, so you basically very soon realize that you have a problem in understanding what your simulation is telling. No, so imagine that your simulation time is relatively short and your dynamic is exploring a relatively simple phenomenon. Then you are able to look at it based on your chemical intuition or physical intuition. But then when you start in a way exploring a landscape, for example, of a protein, and you start exploring okay, so let's see if here this thing is playing. So this is just okay, is an example of a movie that doesn't play, but it doesn't matter because it actually shows that at a certain point you run into the problem of that it becomes practically impossible to look with your own eyes at a molecular dynamic trajectory. So here, so this thing, which is a problem which is not only mine, of course, but it is of the community at large, has actually triggered the development of, well, on one side has triggered the fact that this forced us to learn techniques which were already available for looking at complex data landscapes. On the other hand, triggered further dedicated developments aimed at the specific applications to molecular analysis. Well, actually, some of the techniques which I'm going to talk about today, even if they are inspired and they are actually born in the field of molecular physics, they, of course, are general purpose tools. So one of these tools is actually, well, here let's say that in order really to guide my presentation, I will mostly focus on molecular systems. So here, so the question is, so if I have a very large molecular dynamic trajectory, what do I do in order to understand what's going on? So there are actually two different manners. One is the traditional one, which is I look at an ordered parameter or a collective variable. The thing is the kind of development which I will talk about apply to the case in which I don't know my collective variable. So I don't know what it is going on my system, and I want to discover it from the data. So if I want to discover it from the data, the first thing I have to do is to project my trajectory in a low-dimensional space, and I can use, for example, principal component analysis or collective variables, or things that are more advanced, like isomap or time-independent component analysis. And then, in principle, I should do an histogram. Well, here it's a very quick thing. And then, well, let's say identify the states, assign the configuration to the states, and then eventually I end up with some understanding on what's going on in my system, like a simple one-dimensional diagram telling me how my dynamics is going on. So here, this is let's say a cartoon of an analysis pipeline, well, which is, let's say, morally unsupervised. So here, this pipeline has and still had and still has, despite a lot of progress, many open problems where our investigation is actually still trying to find out how things are going. So here I'm just highlighting some of the problems that are well known and critical. Like, for example, when you do the projection, how do you choose? How can you choose two variables, for example, because you want to visualize your system in 2 dimensions? No, and then let's say that you don't like 2 variables, but you like 10. Great, but then, except for the fact that you cannot visualize a landscape in 10 dimensions, how can I compute an histogram in 10 dimensions? No, so this is my data are sparse in 10 dimensions. That's what one currently thinks. And then there are other open problems. No, so here these open problems are those which somehow motivated my research and actually motivated me and of course also other people independently to develop methods which are aimed at extracting in an unsupervised manner the gross or fine features of a probability landscape in a high-dimensional space. Well, the problem, well, actually, the problem in a 10-dimensional histogram that if you do a 1-dimensional histogram, you divide your variable in 10 bins, and then you count how many data you have in each bin. If you want to do a 2-dimensional histogram, then the bin must be 10 by 10, which means 100. If you are in 10 dimensions, in principle, you have 10 to the power 10 bins. And if your molecular dynamics has 50,000 frames, you will have 0.000001 frames in each bin typically, no? And so you are a little bit under sample. All right. Okay. So a critical difficulty of using machine learning in this field is actually projection without using the collective variables. So here, let's say that this is a two-dimensional landscape, and I want to do a projection, and then I map it to dimension 1 by a linear method, which is principal component analysis, and I'm extremely happy because this thing works great. But then if my landscape, if my manifold is curved, then principal component analysis, even if this thing is two-dimensional, principal component analysis, well, doesn't work in the sense that even if this guy is two-dimensional, I will not be able to map it into a two-dimensional graph. And then people have developed methods listed in this slide, which actually help mitigating the problem. They range from kernel PCA to diffusion map, isomap, and so on, which are all listed here. Okay. So the thing is the following: that if you have if you have a manifold which is curved, you can always think to iron it. But if this manifold happens to be not only curved but also closed, imagine that you clip it here, then the only manner in which you can actually, even if this is clearly two-dimensional, the only manner in which you can map it to a plane is breaking it apart. No, so this is actually a key problem. The key problem is that the topology of the manifold containing the data is typically very, very complex. Very, very complex. If one imagines, so the idea of imagining that your data, especially in a complex molecular system, live on a manifold which is isomorphic to an hyperplane is, if you think about it, a pretty naive assumption, no? And so we are like a more realistic view of a manifold on which complex system live is actually a foam. A foam like this one, where basically most, so if you compute so the dimension of the face of a foam piece is small, but actually the foam bubbles touch each other in places where the dimension is locally larger, and so the system can go in different directions. No, so here, well, here this is actually summarized here in what is like a more realistic view of how a manifold should look like. No, so here curved and twisted, okay, but complex topologies. And then, okay, so the local dimension, which is a number you can really compute. Actually, I will actually sketch on a manner in which you can compute it. Happens to be of order, for example, of order 10. No, 10 sounds like a big number, especially considering what I just told you before. But actually, it's actually small if you consider that we are talking about system like, for example, a molecular dynamic of a large biomolecule, which lives in a let's say physical dimension which is equal to the number of atoms of the system, like order, well, several thousand degrees of freedom. So the fact that the intrinsic dimension is 10 is actually almost a miracle. But okay, so now, well, this is actually where we work. So the framework in which we try to develop, we have tried to develop a pipeline is actually this one. Is since, okay, pipeline for analyzing surfaces, manifold, which are basically practically isomorphic to an hyperplane, was already available. It's very powerful. It's something that one should always try first. But then if this doesn't work, then there is, well, something else that you can do, which has partially been developed in the field of neural networks. But you can also do it in a different manner, which is the one which I will try to sketch today. Of course, I will only give you a sort of a general idea of what are the pieces of the pipeline. Okay? All right. So here, let me skip this thing. Well, this is just an example of what happens if you try to use isomap, which is an ironing method, let's call it like that, to the analysis of a molecular dynamic trajectory of a protein which falls back and forth several times. So you basically get a two-dimensional projection, but this two-dimensional projection, well, basically what you'd like to see here, you would like to get blue points separated from red points. And here, this thing, they are clearly mixed. And so this thing is not very informative. Okay, well, here, I like this picture because it reminds me of my foam-like landscape. So this is, well, let's say Marshallese sailors actually build maps that look like that, which have nothing to do with, one might be willing to think that this thing is just a map of the islands. This is actually not the case. So this map contains, in a sort of a synthetic manner, the information about, well, the position of the islands, of course, but also the main direction of the currents between the islands and of the winds. Don't ask me how, but yeah, but okay. Okay, so here, so our let's say perspective on let's say unsupervised data analysis is well, of course, it's not only our perspective. Let me be clear; it's just a possible different perspective from the one of principal component analysis. Is this one? So we start from the assumption that okay, so data are generated from a high dimensional probability distribution. What we actually assume is that the support of this probability density, the probability distribution, is a manifold, which has a dimension which is actually lower, much lower than the number of coordinates of my system. So this is the only assumption which we are actually trying to do. We, since we sort of assume that the topology of this manifold is very complex, we do not attempt projecting the data on a low-dimensional manifold. No, we don't even try. Instead, what do we do? So instead, well, we basically have developed a framework which allows estimating the probability density on this manifold without defining explicitly the coordinates of this manifold. So basically, the idea is really like, instead of trying to construct what are the coordinates and then computing the density afterwards, as we were doing in the initial pipeline, no? First projection and then histogram. Here we do a different thing. We basically compute directly the density without performing an a priori projection. Okay, so here this is just the general idea, and then basically we are able to identify automatically, let's say, the critical points of this probability landscape, where critical point means basically the probability maxima, and well, let's say the saddle point connecting these critical points. Okay, so here, well, this is just an example. If you have a probability density in 2 dimensions looking like that, and then you harvest like a few thousand points from this probability density, then you have like, these are my data points, which in a real world case would live in a very high dimensional space. And then we basically are able to identify somehow the probability peaks in this data set. And then we build compact representations of how these peaks are organized. So basically in this compact representation, for example, in this one, you have that like the spheres are proportional, the radius is proportional to the size of my cluster, and the connections the thicker connection are those among the clusters which are more connected among each other. Okay, so this is just a possible idea, but the idea is really to look at a projection where the only information which is conveyed is 1 point for each probability. So the thing is, of course, strongly inspired by molecular physics, where basically each of these points will actually correspond to a conformation. Like if you look at this in a system where in a solid state physics system, for example, let's say a polymorphic crystal, each of these points will correspond to a different polymorph. All right. So, yeah.
So you do before doing the reduction, you find the density. So
well, we are now going to see exactly what we are doing, because now I haven't yet told you exactly what we are doing.
so there is so the problem that we were talking about.
Well, in principle, if you do, so this problem remains. We are going to see how we are going to solve it, to mitigate it. So here I haven't yet told you what we have done. All right. So here, okay, the first key ingredient of this pipeline is estimating the dimension of the manifold containing the data. This is actually really a key ingredient. So it's the only key ingredient. Why this is a key ingredient? Because basically, in order to know what is the density of my data point, I need to know at least locally what is the dimension of the tangent plane to my manifold, right? So here, the intrinsic dimension is exactly this number. This actually is what tells me how many points I should expect in a given distance. If I don't know this intrinsic dimension, talking about density doesn't make sense, because the fact of having 1,000 points within 1 angstrom has a totally different meaning if my data points are in a 10-dimensional space, or in a 100-dimensional space, or in a 1-dimensional space, right? Okay. Here then, well, we estimate the probability density of each data point, and then we find the probability maxima by density B clustering, which was already mentioned by Alex, I think. So here I will actually go quickly, and then we proceed to other things. So here, since I don't want to, did also Alex mention about the estimate of the intrinsic? I will tell you just something very briefly. So this is actually a really key ingredient of anything we are doing. So this is something which I have to say that this really changed so the fact of realizing that it is first of all possible, and second useful, estimating the intrinsic dimension of the data manifold is really something which was an important game changer in all the approaches that we were doing. So the intrinsic dimension is the minimum number of parameters required to describe the data with minimal information loss. No, it doesn't mean zero information loss, because you always have noise in the transverse direction, or but minimal information loss. So here there is such an important quantity which many works have actually been devoted to estimating it. Okay, so the most famous manner of estimating it is actually dates back to the 70s, and is something which, in the 70s was called an estimator of the fractal dimension, right? And basically, so the general idea is simply counting how does the number of data point scale with the distance, right? Basically, if you do a log-log plot of this thing, the slope in this log-log plot will be exactly equal to what we call the intrinsic dimension. What is the problem of this equation? The problem of this equation is that you have a prefactor. This prefactor is rho I, right? So here, if rho I is approximately constant, or basically most of your points are in a region where the density is approximately constant, then no problem, you can directly use this one. But if the density varies from point to point, as it happens for any instance in molecular system, and you compute a global histogram of this thing, mixing points of different density, you are actually mixing the estimate of two different quantities. One is the intrinsic dimension, and the other is the density. No, they are actually wrapped together. So if you simply do a global histogram, you are not able to disentangle this estimate. So one of the things, so of the first contribution that we did in this field was actually developing an approach which allows to disentangle the two estimates. So you first estimate the intrinsic dimension, and then after you know the intrinsic dimension, you estimate the density. So here, so of course I don't have time to enter into the details, but actually the key idea is of looking, instead of looking at the probability distribution of the distances, where I have a prefactor rho, I look at the probability distribution of the ratio between distances. This is the ratio between the distance of the second neighbor and the ratio of the first neighbor. Basically, in the probability density of this quantity, which is dimensionless, the density prefactor exactly cancels out. So here the idea is doing inference on the value of the intrinsic dimension, looking at the probability density of a quantity which is dimensionless, and it is, let's say, at first order invariant with respect to variations of the density. So in this manner, I can basically mix together measures of this same quantity here in region of my data landscape, which have a different density. Okay? So this is the general idea. Yes?
Just a very naive question. How from your data to recognize who are the neighbors? So
I need the distances. So the key ingredient, the only ingredient that I have in all the methods we are using, we are not using, so we are just doing things computing only distances.
Okay.
So that you need to define a metric, a distance.
Before, and then you do this.
Exactly. So given a metric, then this metric in a way implies the fact that you can estimate all our quantities. Even the densities, as we will see, requires, of course, estimating the distances. But the key thing is that we estimate distances, assuming basically that these distances are, so basically that my data are contained into a tangent hyperplane. So basically, for example, if I want to compute an angle between two data points, either I know the coordinate and then I do the scalar product, or I compute the distance between this, and I do use Carnot theorem. So basically, there are many quantities which in principle you can compute, but basically most of the quantities that you can imagine, you can compute using only distance. This is actually the key point. Nobody, and in fact, we have well here. So first of all, the intrinsic dimension in any problem that you can imagine is scale dependent. So actually here, even in this simple example, at the small scale, it's two-dimensional, at intermediate scale, is one-dimensional, then it becomes two-dimensional again. And second, it of course depends, well, there are cases in which it depends on the position. Like for example, in an order to disorder transition, typically the intrinsic dimension is different in the two phases. No, and then of course it is important to develop estimators which allow us assessing if your data justify the assumption of saying that your implicit dimension is constant or not. So this is things on which well, we are working, people are working, and these are very, very important, but for the moment, I'm not going to talk about it. Okay, so here I'm going to skip over that. Here, well, I know that I don't have a lot of time, so I only really want to give you a general overview of what are the ingredients, and all of these ingredients is actually not a totally simple one. So now the key thing is how do you estimate since the intrinsic dimension of, for example, if you have a protein folding trajectory, the intrinsic dimension which you typically get is of order 10, how do you manage to compute the intrinsic dimension in 10 dimensions? No? So this is actually a key point. So the first thing is that yes, so that it is possible. Now the density estimator and the free energy estimator which we develop are actually reliable in a dimension, in intrinsic dimension, which is, let's say, up to 20. Let's say 10 for sure. How does this thing really happen? So the reason how this thing happens is, well, first of all, we do not do histograms. Because if you would try to do histograms, then it would be totally impossible to cover your space with cells. And then, okay, so here, so the first key ingredient of our free energy estimator or density estimator is a very, very important and famous method, which is called the k-nearest neighbor density estimator, which works in a very simple manner, which is this one. You basically set a meta parameter of your approach, which is the number of nearest neighbor. Here is 13. And then you basically find the 13th nearest neighbor. And then you basically measure the volume of this sphere which contains your 13 neighbors. And basically you say that your density is equal to 13 divided by pi divided by r of the 13th neighbor to the power 2, right? Okay, so this 2, who gives me this 2? This 2 is the intrinsic dimension. So here, if I don't know this intrinsic dimension, and here I put the number of atoms, then I get a number which is totally meaningless. This is the first well, important ingredient. Okay, so here this very important ingredient, however, is a pitfall, a very important and famous pitfall, actually. So this pitfall is that if you have a highly non-trivial probability density, where your probability density is somewhere flat, like here, and somewhere it varies a lot, like here, then the best possible value of this meta parameter k, which we mentioned, is different for different data, right? Here I would like to take 20, because otherwise if I take a larger point, I end up in this region and I do systematic error. And here I would like to take instead a very large number because the density is flat, right? So the key thing, the key, so here, so this thing is well known. And since it is well known, people have actually devoted a lot of work to try to address this thing. And here there is a vast literature of how to find a compromise between what is called the bias variance trade-off. So means that you want to make your estimate using as many data points as possible, because you want to reduce the statistical error, but not so large that you introduce systematic error. Well, most of the literature on this field has actually been developed in a framework in which you know the coordinates. Here we don't. Here, let's say our contribution to this field is the development of a method, which of course builds on previous results, which is specifically devoted to estimating the density on an embedding manifold, which has a dimension which is much smaller than the dimension of the ambient space, and assuming that I'm not able to find a local map of my manifold. So this is exactly the point. So typically people what try to do is to build first a local map of the coordinates and then estimate the density afterwards. We don't try to do that. So we really keep our coordinates, we only compute distances. Okay? Please stop me. So here the key ingredient of our method for estimating the density or the free energy, which are equivalent objects, because the free energy is the logarithm of the density, is finding the optimal value of k for each data point. How do I do that? So basically, I do that starting from a very small k and asking a question. We do it in a statistical framework. The question that we ask is, should we include the next neighbor in the density estimate? So this is the question which we ask. So we try to add another one, no? And here, how do I try to reply to this question, if I should include this extra data point or not? How do I do that? I basically compare two hypotheses. So this is just like a statistical setting. I compare two hypotheses. So the hypothesis number one is that the point I and point and its case neighbor have different densities, right? And the hypothesis number two is that they have the same density. Basically, these two hypotheses are basically, I reject hypothesis two when a likelihood, which can be explicitly defined, of the hypothesis one becomes much larger than hypothesis two. Of course, this thing, well, here it's a little bit of, well, naive and then wavy, but can be put in a rigorous statistical framework of model selection, which is what we do. Well, when this happens, basically, when this happens, the size of the neighborhood of I is optimal, in the sense that I cannot make it larger without violating an hypothesis, that the density is constant. So actually this thing, well, here, this is just a small movie that shows that you increase this neighborhood more and more, and this is the difference between the likelihood of the two models. And then at a certain point, when I start reaching these high density regions, I violate this hypothesis, because in fact you see that the hypothesis that the density here is the same as the density there is actually violated. So needless to say that if I didn't know that the dimension of this space is 2, this test would be totally meaningless. Okay, so here, well, here that's the result of what we do. Of course, it is. So here there is a little bit of math which I haven't shown. Here I'm not totally sure that I'm going to show you much more math. But okay, so here this thing, well, actually works, and this thing actually allows, okay, not only estimating the free energy, which is the logarithm of the density, but also estimating the error, because we have a statistical model underneath that, and we basically estimate the error on that using Fisher information theory, basically. Basically, the curvature of the likelihood in the maximum, to be a little bit more concrete. So this thing, well, so these are just some benchmarks which show that even in relatively high dimension, now we have benchmarks in even higher dimensions. So this is a correlation plot between the true free energy and the estimated free energy with our estimated error bar. And this is a comparison between basically the probability distribution of the difference between the free energy, true free energy, and the measured free energy divided by the error, superimposed with basically a normal distribution of average 0 and variance 1. So basically we are very happy because, as you can see, this means that our model, also our model of the error, match what we wanted, because this thing is somehow pretty much Gaussian, even in pretty high dimensions. All right, so with this, I think I'm almost running out of time. When did I start?
Yeah, 5 minutes.
Okay, so here I'm not going to talk about probability, well, density peak clustering, because this is something which was already mentioned by Alex in his talk. And I'm not even talking about this one, even if it's interesting, because it's, so this is like a geometric procedure for finding the zero point, right? Finding the maximum is one thing, and another thing is how to find the zero point if you have like an array of data points. And of the data point, we only know the density, right? So this is something which must be addressed, and we have tried to find a solution. But okay, so here now let's go to some applications. Here there are two applications which I want to show. So one thing is an application of this whole approach to a very simple molecular system where you basically have 8 metastable states. So this is like a trialanine, and these are 8 conformers. So basically, let's say one of the manners of analyzing this system is by building a kinetic model which requires analyzing a trajectory, estimating the transition probability matrix between a very large number of microstates, and then studying the spectral property of this transition matrix. No? So this is a very a pretty complicated approach which requires a lot of data. We are basically so the density peaks which we are able to find with this pipeline, whose key ingredient is actually this manner of estimating the density peaks basically map one-to-one to the Markov states. So the Markov states are these conformations which are metastable. So this was actually one of the first tests that convinced us that what we were doing was compliant with kinetics, because this is actually what it is absolutely necessary to have if you use such systems for analyzing, for example, a molecular dynamic trajectory. So the density peak clusters found using this pipeline, basically, even if you are not looking at the kinetics, because we don't use in any manner the fact that our trajectory is a time-ordered sequence, they are actually equal to the Markov states in a Markov state model. So here, these are tests on, well, here I'm not going to enter into that, but basically, so this thing has been benchmarked on systems of increasing complexity. But here I want to spend the last 3 minutes, which I have to mention a very serious problem which we had until 5 years ago. And then, well, there has been something which, in my opinion, is really a breakthrough, in my opinion, at least in our field, which is actually due to the contribution of Giulia Sormani, who is now working here at ICTP. So this thing arised from the following problem. Okay, so this is the analysis of a protein folding trajectory. So a very long trajectory where several folding events are observed. Okay, so here the first thing, one thing that we can do is the following. We find that the trajectory is embedded in a manifold of intrinsic dimension 12. And okay, well, actually, if you look at things in detail, you discover the intrinsic dimension is slightly different in the folded state and in the unfolded state. But let's forget about that for a moment. Then here, this is a plot where here on the y-axis I have the free energy, and here I have the distance from the folded state. This is Q is equal to 1 if my state is folded, and 0.3 if it is unfolded. No? What do you see here? You see a funnel. So a funnel means the more you go towards the folded state, the lower is your free energy. Okay? Okay, here you clearly see that there is absolutely no barrier. So even if your system is clearly metastable, because if you try your simulation, start the simulation in the unfolded state, it will remain unfolded for a very long while. Still, there is no barrier, or almost. This is one dimensional. Well, but okay, here I'm going to show you that is actually this is actually 1 point. But now, let's say that I apply my pipeline, so I forget about one-dimensional projections, and I try to find out clusters on these. Where are these clusters? So here Where are these clusters? So the thing is that basically all the clusters are here. There is nothing there. Very, very small stuff, which is basically totally statistically unreliable. So basically, if you analyze this trajectory blindly and you don't know Q, you are tempted to conclude that you have only 3 metastable states. All these 3 metastable states are actually folded, because look at the value of this. And basically the barriers, the transition barriers between these are actually very small, because these are just defective folded states. And then you have basically thrown away the most important metastability, right? So this is a problem, right? Is a problem. So the key thing is that no cluster in the unfolded region. Well, does it mean that the unfolded state is not metastable? But then, why is folding a rare event? Well, actually, this question is a question which we typically ask at the entrance exam of our PhD, because it's a very trivial, it has a very trivial solution, no? So here, look at this system. So this system is a system where it is a potential energy landscape, where I have a minimum here, and then a flat region there. Now, basically, the flat region there works like an entropic trap, right? So you basically, it is metastable, not because it's a minimum, a local minimum of the potential, but because it's large, right? So here, if I am here, I have to diffuse a lot in this region before finding this tiny little bit. So this thing, which looks pretty simple to find this minimum in 2 dimensions, of course, if I am in 12 dimensions, it becomes very easy. So this is what determines the fact that my folding event is rare. Okay? So here, only one cluster. Of what the problems we are addressing here. Well, these are just few conclusions on well, some of the things that I told you. And with this, maybe I leave some room for question, and I thank you for your attention.
Okay, so thank you very much for the very clear and exciting talk. Of course, we have a lot of time allocated for questions, so please start asking many. Who want to start?
Let's start with so two curiosities. The first is how the metrics, how the choice of the distance modify the determination of the distance. Do may depend, or in practice not so much?
Okay, so this actually opens, you're opening a Pandora box, because, okay, on the same data space, you can define in principle many distances. And in principle, many distances. What I'm really working on at the moment is exactly how to compare the relative information content of different distances defined on the same data space. And in practice, saying if I have 2 distances of the same data space, typically one has to choose the distance which allows making prediction on many other distances. So here in all of, so this is a very, so it's something which I find extremely interesting, because it's also related to the study of causality and many other things. If you are curious, I would be very much happy to discuss this thing with you. Here in all these applications, we basically, the distances used to make the analysis is a distance defined in a relatively large dimensional space, but whose choice is guided by domain knowledge, right? For example, if you use, like you study a protein, you can use the dihedral distance. So you basically compute the difference between all the possible dihedrals defined in the structure of the protein. Or you can use the contact map distance. Like, for example, in the specific example of the protein, the two matrices give the same information. And so if you do the analysis with the two matrices, you find basically similar results. But this thing is absolutely not guaranteed. It's an open problem somehow.
Some curiosity, this more the real curiosity does make difference if the dimension is integer or really
Not in our estimator, because in our, so the key thing is how the dimension enters into the definition of the likelihood. So it's just enters in two different pieces. It's just a number that you multiply by the logarithm of another number. So if this thing is integer or not, it doesn't really matter.
If your data for some reason are fractal, so things like this, you wouldn't see that way.
Well, the thing is that you compute a number, and this number is in general never an integer.
Yeah, but
but the thing is, how do your, so the question is, how are my results stable with respect to relatively small variation of these intrinsic dimensions? So the key thing is that, of course, if my system is 10-dimensional and I tell you that it's 3-dimensional, then I will do horrible mistakes. But if I tell you that it is 8-dimensional or 11-dimensional, then basically so you are almost not able to see an effect.
Also 10.5,
let's say. Well, say if you go, let's say, yeah, 30%.
Other questions?
So, from your analysis, then you wrote down, or you mentioned kind of master equation to discuss the dynamics. Now, you need extra information to infer the type of dynamics. So, I guess in this case, it was the structure of peaks.
Well,
or
not well in the sense.
You can reconstruct the.
So the thing is the following: that you typically, since your peaks are basically free energy, okay, let's say free energy minima in a very high dimensional space, where in principle I haven't thrown away any relevant information. Therefore, you can estimate the rate using trivial transition state theory. So
exactly, I was asking if you have totally different system.
Well,
in which
no, the thing is so the reason why transition state theory typically fails, well, not typically, well, if a chemist was sitting here would probably kill me. So the thing is that in many cases, so the typical manner in which we estimate a transition time is by computing the free energy as a function of an order parameter or a collective variable, and then you measure the height of the barrier, and then you say that your transition time scales with the exponential of the difference between these two. No. So the point is that this thing can be very wrong if you choose the wrong order parameter, right? Why? Because it's a problem of projection. So here, if you have like if you have a system which is 2-dimensional, which basically looks like that, and you take this collective variable, then you basically project it in this direction and you find a very small barrier, right? And so you go totally wrong. But if your free energy minima are actually built on a support, are defined on a support, which, so by definition, within our definition, you are basically not projecting anything relevant. The barrier height, which we measure, is meaningful and can be safely used to estimate the transition rate. That's somehow the point. But okay, on the other hand, clearly in our, okay, where are we? In our
the thing is that
Oh, che bello.
Devi vedere il modello a presentazione.
Okay, well, it doesn't matter. I wanted just to show you that, of course, in our analysis, then you can exploit time ordering a posteriori and estimate the mean per passage time and everything, and actually check if the numbers that you are getting are consistent with what you expect.
Other questions?
So in order to do that, you need to sample something in the.
Yeah.
Otherwise.
Well, absolutely yes. And the thing is the following, that in fact, these trajectories which we analyze typically perform, like let's say you need at least 10 transitions between the two states before having a statistical reliability which is sufficient to do this thing. Who gives you this trajectory? Well, of course, either, so the thing that we did here was simply downloading it from the web using David Shaw stuff, but otherwise you have to use enhanced sampling techniques. And this is, well, actually how to use this thing in conjunction with enhanced sampling technique is another important story, because here we are always assuming that our points are harvested independently from a given fixed probability density. So if you use enhanced sampling techniques, you must use reweighting techniques in practice.
Yeah.
To do this.
But it's something that people do.
It's something that people do. Well, let's say that I don't think that many people are using our approaches except me, my closest relatives and friends. But okay, we are trying to go in that direction. Let's put it in this class. Okay?
I have actually a question. So at the beginning of your talk, you mentioned that for some of the algorithms you develop, you only need distances, right? So in a sense, you don't even need to know the dimension, that was used to compute those distances.
In fact, well, this is actually a very important observation. We have used successfully this algorithm to do clustering of all the known proteins. So basically, if you looking only at the sequences, no? So you basically, we clustered 20 million sequences, and the distance between two different proteins is actually computed by doing a dynamic programming alignment between the two sequences and counting the number of matches. So here the coordinates are absolutely not defined. And then based on this distance, you can actually apply the same pipeline. And in that case, you actually find something of the order of 40,000 free energy minima. Okay. And each of these 40,000 free energy minima correspond to what people call a protein family. So basically,
so that would be your true intrinsic dimension? Then?
No, the true intrinsic dimension in this case is of the order of 5.
Okay.
5 is the number. So 5, what is the meaning of this 5 in a protein space, in a sequence space? It means that if you actually look at the sequence, and then you say, okay, now let's see other sequences which differ by a significant number of mutations. So in principle, you can imagine that you can mutate independently each amino acid, but this is actually not the case. You have evolutionary constraint such that mutation, if you do 10 mutations, you have, let's say, a correlated events such that the linearly independent directions in which you can actually do a mutation are actually only 5 and not equal to the number to your.
Like saying, so if you move randomly atoms to build the molecules, 99% or 99.999% of what you get doesn't make sense.
Doesn't make sense, exactly.
So
this is exactly the point. Like if you do a, well, let's say Monte Carlo move, either they are very small or they are rejected, no?
Okay. Other questions? Yeah.
So, is there a qualitatively, I think that there should be a connection between entropy and the visible somehow?
So I think the connection, well, somehow, yes, because the entropy is, well, one of the possible formulation of the entropy is the logarithm of the volume of space around the point where the properties are identical. No, if you say I have a state, a microstate, and I say, okay, now I can travel around and I can move in many directions, and the macroscopic properties do not change, and these are what I would qualitatively define as a microstate. Now, what is the entropy of this microstate? Well, it is actually the volume in phase space which corresponds to this set of configurations. No? So in order to compute this volume, well, of course, you need to know the intrinsic dimension, no? Because otherwise, if you simply know the maximum distance that you can travel from that point and still your property remain the same, then you have a completely different meaning if you have a physical constraint which allow you to move only in two directions, or you can move everywhere, right? So they are related.
Okay, maybe one last question. Anyone? Okay, if not, I ask the last question. It's very, very technical. So you mentioned you have a package for all of this. So is it like an open source
Yeah.
code?
Yeah, it's called DadaPy. I don't know why. But okay. Well, it's actually, well, there was at a certain point the link for the, okay, so this doesn't work, but okay. It's
presentazione presenta su tutto.
presente, sì, hai ragione. Where is my mouse? Tu lo vedi il mouse? Because it's on the other screen.
Okay.
Okay, well.
It's in your tool.
Yeah, it works.
Okay.
Now we see everything.
All right. Yeah, it's something which we developed over the years, and it's just a Python library which is interfaced also with can be interfaced with the scikit-learn. Basically, all these things are implemented here. But since you are not a close relative of mine, I'm totally sure that you're never going to.
Okay, thanks everyone, and let's thank again our speaker. So we have this is a series, so we have another talk by end of March. So in a bit like not in a month from now, but a bit earlier than that, and